Hello all. I hope you're all doing good. I wish you all great health. I'm Krishna Balasubramanian. I'm from the Electric Engineering Department, IIT Kanpur. I thank you for being in this presentation. So let me begin this presentation. Uh, Today I'll be talking about high TC superconducting tunnel diodes for cryogenic temperature measurements. The need for cryogenic temperature measurements have been growing. Cryogenic temperatures are typically from liquid nitrogen and below, and there are a lot of conventional silicon germanium heterojunction transistors which are starting to operate at lower and lower temperatures, starting from cryogenic temperatures and below. There are a bunch of photodetectors, indium gallium arsenide, indium arsenide detectors, which go to low temperature for noise reduction. There are these upcoming qubits based on superconductors, silicon germanium, quantum dots, atoms, all these things operating at lower temperatures, as well as the new generation of semiconducting power devices which starts to use superconductor semiconductor interfaces, all these things requiring low temperatures and cryogenic temperature measurements. The requirements for temperature sensors under these conditions are similar to every other sensor. It has to be precise, it has to be fast and compact, right? They require local temperature measurements and to be integratable, because you can have regions which suddenly get very high temperatures, and these are superconductors and devices which will lose their property if even there's a slight change in the temperature. And they will all like to have magnetic field immunity, because most of the superconductors or qubits, for example, operate at very high magnetic fields which should not affect the temperature sensor. And as I showed, it has to be cheap to fabricate and install uh, and mass fabricate and such. But, so there have been a bunch of sensors which have been used till now. The most common one being the resistive platinum 100 based sensors. They are bulky, they are big, and they are not efficient at low temperatures. Next one comes the ultra cheap type A thermocouples. But they are compact, they are small, they are fast. However, it often requires a reference, and then they are not much suitable because they cannot be integrated into devices. And then comes the most commonly used sensor, which is called the diode thermometers. They are very good in the sense that they can be easily replaced. They are cheap. They have been reliable for some time. However, they suffer from a big disadvantage in the sense that in the temperature range between 10 to 20 Kelvin, most of these diodes based on silicon and gallium arsenide, right, they have this peak in the response. Suddenly, the forward potential, which is used to measure the temperature, starts to have a peak close to the temperature range, which is of importance. For instance, uh, this 10 to 15 Kelvin. And apart from this, there are other sophisticated sensors based on Coulomb blockage, Josephson's junction, infrared thermometry, and all those things, which can be used, but however, they are always cumbersome and have some issues with the implementation, in the sense integratability as well as the cost. The topic of current discussion would be on superconducting tunnel diodes, is what I would like to propose as a solution, which can be fast, which is cheap because it can be easily integrated with the device that has to be tested. Superconductors work as temperature sensors because of the fact that there exists what is called as a bound state between two electrons which have a lower energy than each of these electrons being independent. For instance, if we have two electrons with opposite momentum, right, and at, a, at a suitable temperature below what is called as a transition temperature, they form a kind of a bound state whose density of states resembles this plot. So here I have the density of states versus the energy level here, right? At temperatures below the superconducting transition temperature, the density of states exhibits a gap, in the sense that you have no single particle electron states in the energy levels surrounding or in the neighborhood of the Fermi level, right? And then at the edge of particular energies, which is distinguished here as 2 delta, have this exponentially increasing density of states, right? The density of states under these conditions are expressed by this expression, where it is 0 for energy levels lesser than this delta, which is a characteristic parameter called as the order parameter here. And even this delta has a kind of a temperature dependence. So as you reduce the temperature close to the transition temperature of the superconductor, when the temperature is equal to transition temperature, delta is 0, and then it has this slow changing curve reaching to its ideal value at 0 Kelvin. its temperature dependence can be noted to be as given here. So the purpose of this brief introduction was to say that our device, which is a superconductor normal metal, and the tunneling current between these interfaces is what is going to be used to measure the temperature. So let us say that we have a metal at 0 Kelvin where all the electronic states below the Fermi level is completely filled, and if we interface it with the semiconductor as shown here, you can see that the tunneling current is going to be 0, in the sense that there are no states in the superconductor where the electrons from the metal can tunnel into. However, if we increase the temperature, you can see that there are certain energy levels where you can have electron jumping from the normal metal to the superconductor, depending upon the transmission or the transmission probability of this interface. Right. However, to actually calculate what is the transmission probability at the interface, one has to go through what is called as a BTK formalism, where the normal electron is described as a wave function having both an electron and a hole component which are independent. However, a superconductor has an electron and a hole component which are mixed using this Bogoliubov transformation. Right? So you have a U and a V component of the wave function in the superconductor, and you can obviously solve this problem with a very simple boundary condition of continuity at the interface and of the wave continuous wave function at the interface, and the derivative difference should be equal to the impedance parameter H. We go through all these things because it is this H which determines the tunneling probability between the normal metal and the electron, which we will soon show that can be tuned to change the sensitivity of the sensor under discussion. So here we are plotting the tunneling current versus the potential and the temperature for a superconductor which is called as an LTS superconductor, which is called as low temperature superconductor, or a S wave superconductor, where the order parameter is symmetric for all incident angles. So we will show in the next slide what we mean by this, in the sense that we can say that for any K of the electron which wants to tunnel from the normal metal to the superconductor side, we have a constant delta parameter, and which is approximately equal to 1.8 milli electron volts. There's a mistake, it is milli electron volts for niobium. You can see that the current is almost zero when the bias potentials is lower than this order parameter, right? So, and as you raise the temperature at any given potential, you can see that the Fermi distribution, the electron distribution starts to soften up, and you can have energies, electrons with certain energies higher than the energy gap, which can be tunneled depending upon the transmission probability, right? But then you can see that the distribution of IV characteristics across this particular junction for various temperatures doesn't seem to be evenly distributed. Right? For temperatures at very low, until temperature that you reach the transition temperature, you can see the tunneling current is very low at bias potential, which is much smaller than the order parameter delta. Once you go close to the superconducting order parameter delta, then you have a very good sensitivity. There are certain problems with this LTS sensor. One is being the sensitivity being strongly bias dependent. So it depends upon where you have the Fermi level of the metal. It has small operating temperature range because the typical transition temperature of a low TC superconductor is less than 10 Kelvin. Right? It has strong magnetic susceptibility. I'm not going to prove it here, but then most low TC superconductors have low critical magnetic field, something of the order of 100 milliteslas. And it has self-heating effects because of the fact that you need to bias it at higher potentials to have better sensitivity. So to address all these things, we think that a high TC superconductor has advantages more than the just obvious reason that it has a higher transition temperature and hence a longer range of operation. It has another advantage in the sense that the order parameter is no longer spherical. Here we show a schematic diagram of our proposed device. So we have the superconductor in orange here, and then the normal metal in black, right? So we have two conditions. This is the typical schematics of our device. But then the interesting part here is the order parameter symmetry, which was spherical in the previous case. An unconventional superconductor has an order parameter which is D wave, or it can be D plus S wave, or these are the things which are still being explored. Right? So what it means is that it depends, the delta or the gap in the density of states depends upon the incoming electron angle, which is shown here. So if the electron is being normal to the interface, then it has a different delta, whereas the electron which is incidentating at a different angle, right? So and we can expect the electron to be incident of the interface from all possible angles. So the average density of states turns out to be something as you can see here, which gives you states in the superconducting gap, which depends upon the energy, right? So now you have a density of this which is almost linear near the Fermi level, and this can actually help us to get a very linear and a very gradual tunneling current, as we will see below. Right? So here we are plotting. So previously we did the same thing as we did here. So instead of taking an LTC superconductor here, we have taken an HTS superconductor with the order parameter as we shown, and then we calculated the actual current based on the BTK formalism that we showed before, right? And then we calculated the current versus temperature for various potentials, and you can see that the lines are much more well behaved than what we saw before. It is not clubbed or it is not crowding in a particular region. You have very well distributed I versus T plot, right? And most of them are well behaved at for all potentials lesser than the superconducting order parameter delta. Right? For values which is about 0.1, you can see it is very smooth and well behaved. And even in this I versus potential IV for various temperatures, you can see them evenly being distributed. We calculated the sensitivity. The minimum temperature that you can resolve is basically the voltage resolution that you have of your meter into the actual slope of the dV by dt, right? And the sensitivity can be calculated irrespective of the resolution of your voltmeter, right? So that we can say we can always change. But then the intrinsic sensitivity of the sensor depends upon this EST, which is purely a material parameter, right? And we calculated this EST and then we plotted it at various temperatures. And the lower this ST is higher your temperature resolution that can be, as can be seen here, right? And we can see that our HTS based temperature sensor has very low sensitivity or very low ES close to the operating region of interest, and which makes it to have better resolution at lower temperatures. And this sensitivity can be tuned by changing the interface impedance. You remember the one that we said before, the H. It can be tuned by using the different bias potentials as well as the superconducting symmetry in order parameter. This can be changed by choosing the different superconductor. There are a bunch of IT superconductors. You can choose different ones for these purposes. We actually made some measurements, and you can see that the current versus bias for an IPCO film grown on top of gallium nitride. So we just took IPCO and then slapped it on top of gallium nitride and then measured the IV characteristics at different temperatures, and you can see that this matches very closely to the previous plot that we shown, and even the conductivity matches pretty well to what we expected. So in summary, we show that the HTS based tunnel junction provides a smooth voltage temperature relationship or wide range of temperatures. It is unaffected by a magnetic field. Typically, let's say IPCO has unaffected currents for up to 2 to 3 Tesla, which is very high magnetic field. It has enhanced sensitivity at low bias potentials, as we saw before, and because it can operate at low bias potential, it has low self-heating effects. It can be easily integrated because it can be vacuum deposited. There are the deposition techniques of IPCO are well mature, and it has wide scope of investigations into unconventional superconductivity like pseudo gap, bound states, and such, because it is a device which can incorporate a scientific novelty into a technological one. With this, I thank you for your attention and I'm open to questions.